Hello everyone, my name is Petar, and today I'll be talking to you about deep reinforcement learning. Yeah, it's quite a buzzword. So today I will go from first principles and introduce reinforcement learning, deep neural networks, combine them together into deep reinforcement learning from first principles in a bottom-up fashion. It's one of the major success stories of reinforcement learning. How many of you have heard of the DeepMind Atari player or AlphaGo, or both? Yeah, most of you. So it is definitely one of the biggest success stories of deep learning, and in fact, in my opinion, it's the most fun you can have with deep learning if you're into video games. And these two papers, the DQN paper and the AlphaGo paper, are sort of the two examples that I like to give always about the success of reinforcement learning in the past. And I hope to pitch this talk in such a way that you will not really need to have any prior experience or knowledge of machine learning. So let's get going. As you might know, there are three flavors of machine learning that you might want to engage in. You have unsupervised learning, supervised learning, and reinforcement learning, which we'll be talking about more today. So we start off with unsupervised learning. We have our agent that wants to learn something, and we have the environment. And in this case, the environment just gives you a bunch of data. It doesn't give you any labels, any sort of something that you can attach to this data. You just have a bunch of data, and you need to conclude something interesting about this data. So it's kind of like exploratory data science. You can think about it as, for example, if you gather a lot of data from a lot of people that are suffering from the same disease, and you see that their data points kind of form independent clusters, you can conclude that there are, in fact, different strands of the disease that we didn't know existed before, and then you can also come up with a nice decision rule to tell you which type of disease this is. So think of things like different stages of cancer and so on. So the environment gives us a bunch of data points, x1, x2, xn, and our agent just has to spit out some interesting features or some interesting structure to the data that wasn't known before. In supervised learning, this is arguably the most popular flavor of machine learning today, is the one where environment gives you a bunch of data, and it also gives you a ground truth answer that it wants to hear when it gives you this data as input. So essentially, the environment wants you to learn a function, and it gives you a bunch of inputs and outputs for that function. And this data is commonly called the training data. Once the model consumes this data and figures out what the underlying function is somehow, the environment can then give it new examples it hasn't seen before, and the model is expected to give new answers which are supposed to generalize well from these known examples. And one typical example of supervised learning is if you're giving credit, you want to determine whether or not a person will be likely to return their loan, and based on their previous credit history. And this is a very common supervised learning problem. In fact, you might have access to a large database of previous issued loans and whether or not people have been able to return them. And you can use this information to derive a model which tells you for any new incoming client whether or not they'll be able to return. And in fact, in 95% of the cases when you make a loan application, your application is not really seen by a human. Usually it's all done with a computer, but just for safety purposes, you have a will definitely return, will definitely not return, and don't ask me anything, I'm just a computer. So then actually a human can look at it afterwards. And finally, a reinforcement learning environment gives you arguably the most freedom out of the three options. In this case, you are actually acting on the environment and changing it as a result. So you are in some initial state, and then at each step, you can perform an action on the environment, and the environment will respond by giving you a new state and giving you a reward. And your job is to figure out a way to perform actions such as to maximize your expected returns, your future rewards. And a very typical example is playing a video game. Your states are what you can see on the screen or what's contained in the game's memory, and your actions are the different keys you can press. You can also press multiple keys at the same time, or you can not press anything at this point as well. And your rewards constitute, for example, changes in score. So you want to figure out how to play a game without really knowing anything about it before, just being able to perform actions and receiving new states and rewards. So this is the fundamental reinforcement learning setting. Mathematically speaking, we have a set of states that our agent can be in. This set can be infinite. And we have a set of actions that we can perform. If we're playing a video game, usually the number of actions we can perform is relatively small, all the different buttons that you can press on a joypad or on the keyboard or so on. And there are two functions. One takes in a state and an action and gives you a next state. and one takes in a state and an action and gives you a reward. Now, these are functions of the environment, and they don't have to be deterministic. They can be stochastic as well. And what's important is that the agent has no access to these functions. Therefore, the agent can only call these functions for particular sets of state action pairs it's in, but it cannot reveal the underlying implementation of these functions, so to speak. So the agent has no idea how the environment works. He has to infer it by doing as many actions as possible, starting from the starting state. So once you perform action A in state S, the environment will call these two functions and give you back the next state, which is the state-changing function called on the two arguments, and will give you a reward signal, which is also the output of the function on these two arguments. And the goal of the agent is to learn something called a policy function. A policy function takes in a state and gives you an action. So essentially, given that I'm in this state right now, what is the action I should ideally do to maximize my future rewards? So that's the main objective of reinforcement learning, learning a policy function. So based on what state you currently are in, which action to do. However, we have to be a little bit clever about how we define this thing that we want to maximize, because if we take in just the sum of all rewards and our game does not have a timeout, so it can last forever, then we can have many, many different policies that achieve rewards of plus or minus infinity, for example, and then there is mathematically not a really nice way of differentiating between them. So we also include another sort of a rule that not only we want to maximize our rewards, we want to get good rewards as soon as possible. So we want to somehow prioritize rewards that will come sooner after a smaller number of actions. And to do this, we define something called a discount factor, which is between 0 and 1. It can be 0, it cannot be 1. And we scale all the rewards in the future by a factor of gamma. So the immediate reward we get is taken directly. The next reward we get is scaled by gamma. The next one is scaled by gamma squared, and so on. And this is actually the thing that we want to maximize. And you can see, for example, for different values of gamma, the larger gamma is, the more we value something that comes in the future. In the most extreme case, if gamma is 0, we only care about the immediate reward. We don't care about anything that comes in the future. I won't go into the mathematical details of this, but defining the metric in this fashion is what allows us to assert some convergence guarantees of the algorithms. So now let's think about how within this setting we can determine an algorithm that will help us determine how to play optimally. And in fact, there is an algorithm that mathematically probably can achieve optimal levels of play, provided you can let it play for long enough. So we want to find an optimal policy. And as we mentioned, this metric that we're maximizing is bound to a particular policy P. So this implies that we had some initial state S, and then we performed action 1 given by this policy P. Then we performed action 2 once again using this policy P, and so on. So this metric is parametrized by the policy that we are using. So we want to find the optimal policy is the one that maximizes it across all possible policies. So that's the thing we want to find. And we will also, for convenience, denote the optimal value as the value of the optimal policy. So instead of argmax, it's just max. So overall possible policy, what's the maximal future metric value we can get? And the way in which we derive an algorithm for doing this is defining something called a Q function, which takes in a state and an action, and it gives you the immediate reward you get after executing the action in this state, and the value of playing optimally from the next state scaled by gamma. Directly speaking, what the Q function means is I'm in state S, I'm performing action A. What is the optimal total reward I can get if I do that, and afterwards I play optimally? You can perhaps immediately see that if we are able to learn the proper values of the Q function, we can determine the optimal policy, because the optimal action to play in any state is the one that maximizes the Q function. Does that make sense? All right. So let's take this a few steps forward and note that, once again, the optimal value in any state is given by the maximum of the Q function across all possible actions. And we can factor that in this definition. So we replace this vopt here with the maximization over all possible actions. And this, in fact, gives us kind of a recurrent definition. So we've expressed Q by using Q. And this means, in fact, if we have something that's an estimate of Q, so something that is not the true value of Q, and we've done from state S action A, we've collected a reward, if we update the value of q prime SA to this, so to the value of this formula, based on our current beliefs of what q is, then we will obtain a no worse estimate of the q function. And this, in fact, means that we can start off with completely random values for all the q functions initially, and then iteratively update them as we go along. So we start off with some table q prime that will be filled with random values for all possible states and actions. And as we go along, we perform actions, and then we update using this formula. And eventually, as long as we have some guarantees on how often we can perform each action in each state, we can reach the optimal q values. So we can learn how to play optimally. And this is summarized by the q-learning algorithm. So we can start by initializing this table with completely random values. So we choose some action to perform. We perform it, receive a reward, observe the next state, and use this formula that we've derived to update q prime for this particular state and action pair. And if we haven't reached the end of the game, go back to step 1. So we're in the next state, we can try to do another action and so on. And in fact, this algorithm is guaranteed to converge to the correct q values as long as we visit each state and action pair infinitely often during our training. But let's think about how to choose which action to perform. And this is where sort of the pun in the title of this talk comes into play, is we need to balance exploration and exploitation. Initially, our agent has no knowledge about the world whatsoever. The only thing it can do is play completely randomly, choose completely random actions, and build up its level of knowledge about the environment. But eventually, we would want the agent to become more confident in the values he's computed and use them more to determine which action to perform, and therefore become more likely to find out about complex sequences of actions that will lead to very high rewards. We want to start out with a period where the environment is completely explored, so we just perform basically random actions. But as time moves on, we want to rely more and more on the computed q values to determine which action to perform. And this is a very active topic of research. There are 2 popular approaches to how you might choose an action, and they both amount to defining a probability distribution over actions. So assuming you're in a particular state S, you want to determine what's the probability that I'm going to choose action A for all possible actions. And then you can just sample this probability distribution and play actions from there. So the one I would like to emphasize in particular is the epsilon greedy strategy, which is the one that's used in the DeepMind Atari player. And in fact, what it does is, with probability epsilon, choose a random action. With probability 1 minus epsilon, choose the action that has the highest q value. So that's literally what it is. And you start off with epsilon set to 1. So initially, all of your actions are going to be completely random. And as time goes on, it will decrease more and more towards 0. So you will start to rely more and more on your own actions. Obviously, the problem of determining the optimal schedule of how quickly you're going to decrease epsilon is an open research topic, and it's definitely not unique to to all problems. So you have to be careful and try out many different values if you want to make this work. But this is sort of the basic, because it's the simplest to implement, and it has been found to yield good results. This was the basic reinforcement learning part of the talk. So I've introduced q-learning, and I've introduced how we can choose which actions to perform at each step. Now we have some issues with this, because as I said, this algorithm is optimal, but we cannot have something that's optimal that works nice on all practical problems, right? So something has to go wrong. And in this case, the problem is that the q table is huge. So is often very huge. So think about if you want to play a video game, your states are, for example, all possible matrices of pixels that your screen can assume, or all the possible contents that your RAM memory can have. And I think it should be fairly easy to see that the number of possible states is huge. And therefore, this table of state times action simply isn't something that you can feasibly store in memory for every possible matrix of pixels and so on. So we cannot use this naive update algorithm for most practical problems. The issue is we cannot compute the q table directly. We have to approximate it somehow. And this is, in fact, where deep reinforcement learning comes into play, because we need to find a way of approximating these q values in a memory-efficient way. And something that people have very often been using to approximate functions are neural networks. For those of you who are not familiar with how neural networks work, they are structures of interconnected neurons or processing units that take in some input and give you some output, and they're capable of precisely approximating a wide variety of real functions, assuming you give them enough training data. Each neuron has a very simple mode of operation. It just takes a bunch of inputs, it computes a linear combination of them, and then it potentially applies a function to the result. So the neural network used for DQN and AlphaGo are both deep feed-forward convolutional neural networks, and I will get into a bit more detail about what exactly a convolutional neural network is, but I will first explain a very general architecture, and everything that goes on from there is just a special case. So this is what a neuron is. A neuron takes in a bunch of inputs, x1, x2 up to xn, and it stores a vector of weights, w1, w2 to wn, and it just computes a linear combination of these inputs. So it multiplies the first input by w1, the second one by w2, and so on, and it adds everything together. And then it applies an activation function to the result to inject some nonlinearity into the model. Some of the popular choices for this function are, so you can keep it completely linear, you can use the identity function. A function that has been very popular in the recent years is a rectified linear unit, which simply is sort of an engineer's way of injecting nonlinearity. If your input is less than 0, set it to 0. That's literally what it is. And it turns out that it works quite well. And in both this neural network and the AlphaGo network, this has been the activation function that has been used. So it's currently quite ubiquitous in deep learning. But for some applications, you have still functions that used to be very popular in the past, the sigmoid functions, the logistic function here and the hyperbolic tangent. They're called sigmoid because they have this sort of an S shape, and there is a lower bound and an upper bound, and they can never reach the lower and upper bound, but they sort of have this S shape from left to right. And the logistic function here gives you values between 0 and 1, so it's convenient for representing probabilities. And the hyperbolic tangent gives you values between -1 and +1, so it's more useful for more general problems. But typically, you will mostly encounter this function in most recent deep learning research. And how do you get from a single neuron to a neural network? It's simple. Connect the outputs of some neurons to inputs of other neurons and stack them together and figure out which neurons take in your inputs and which neurons spit out your outputs, and that's it. So the most general such architecture is called a multilayer perceptron, and that's a neural network where you basically stack several layers of neurons, one after another, and each neuron in a particular layer takes in a copy of all the outputs of the previous layer. So this hidden neuron will take in this input and this input and this input, and it will compute the weighted combination that we talked about before for its own weights and give its output and so on. So we have some inputs, we have a hidden layer in the middle that learns some feature representation of the data, and we give some output values based on those. So this is the most general and most powerful neural network architecture. It is unfortunately not applicable to some practical problems such as image recognition, but I will get to that in a few slides' time. What you need to know is that most of the neural network architectures you will encounter are just a special case of this completely unrestricted architecture. So what do we mean by training a neural network? We want essentially to determine what these weights are. So the neuron will start with some weights initially randomly assigned, and we want it to learn good weights, the ones that are going to get us closer to approximating the correct function. So we have known input and output pairs, and the training algorithm will adapt these weights to maximize predictive power, first of all within the training set, but we also want to apply some techniques to make it generalize well outside of the training set as well. And how it does so is it starts from the output neurons and computes the errors. So we have an input and an output pair. We feed the inputs to the network. We get the outputs back. We compare the outputs to the true ground truth values. And based on that, we have some measure of what an error is. And we can propagate this error backwards from the output neurons to the input neurons and modify the weights appropriately. And this is the essence of the backpropagation algorithm, which for deep learning is more popular in a stochastic gradient descent flavor. I will not go into detail as to how these algorithms are derived, but if you want to learn more, these two terms are basically the ones you should be looking for. One interesting fact, because I want to sort of motivate why deep learning is called deep learning. It was proven that if we have a neural network with just one hidden layer and the sigmoid activations such as here, we can actually arbitrarily precisely approximate any bounded continuous real function if we have the proper weights. This is known as Sabenko's universal approximation theorem. What it means is that if we have access to correct weights, we can approximate pretty much any function of interest with just one hidden layer. Unfortunately, the proof of this theorem is not constructive, so it does not give us a nice training algorithm that we can use. And the gradient descent algorithms that I mentioned just now are not really powerful at handling wide networks like that in a correct way. And in fact, they can get stuck in unusable local optima, and it's just not feasible. So we have tried the opposite approach. Rather than having one very wide layer, let's have many smaller layers. And that's exactly what deep learning is. So whenever you have a network with more than one hidden layer, so if we stuck another hidden layer in here, we would technically have a deep neural network. Everything which has more than one layer, aka more layers than you really need theoretically, is what is called deep learning. So in reality, it's not really something that's heavily sophisticated. It's just a neural network that has more than one hidden layer. Now I've come back to the point where I said that even though MLPs, the multilayer perceptrons, are the most powerful neural network architecture, they are not really feasible for a lot of tasks that might be interesting. And a particular one is when we're dealing with large structured data, such as images. And in this case, we will be dealing with images, and therefore, this is quite important. As we mentioned here, each neuron in a hidden layer gets a copy of each of the inputs. That means you treat each of the inputs independently. But when you're dealing with an image, the individual pixels in an image are not really independent. You have usually a lot of correlation between neighboring pixels. So therefore, treating each pixel completely independently is not really something that you should be doing. A typical response to that, the solution to that, and what brought convolutional neural networks to the stage, is to, rather than learning a bunch of weights which take in each individual pixel, to learn something called a convolutional kernel, and then apply an operation called a convolution to the image, which will extract some useful features of the image, and then we can, once we've extracted enough useful features, we can make the image smaller and smaller, and finally we get it to a small enough size that we can use the fully unrestricted approach that was just mentioned. So this convolution is essentially you have your image, and you train a small matrix called the convolution kernel. You overlay this kernel in all possible ways over the matrix, and you record a sum of element-wise products to get a convolved image. And this is what it looks like. So we have an image, we have a kernel, and we have the convolved image with the kernel. So this is what the neural network wants to learn. It starts off with a random kernel. After some training time, it's going to learn values that are going to help us extract useful features such as edges from the image. This is just an example. We want to compute the top left field of the result. It takes in the kernel and overlays it here, and it essentially takes all the possible element-wise products of the image with the kernel and sums it all together. So here we have this pattern which will recognize fields here, and it will completely ignore fields here. And the only match we have is in this top right field. So essentially the result is just going to be 1 because everything else is 0. If we want to move on to the neighboring fields, we just slide this kernel across in all possible ways. At each step, we overlay this kernel over a region of the image. For each field, we multiply the respective fields, and we add them all together. In this case, the result is 4 because we have a 1 here, we have a 1 here, we have a 1 here, and we have a 1 here. Those added up together give us 4. So this is essentially what a convolutional layer is, nothing else. Just train a really small matrix, overlay it in all possible ways over the image, and compute the result. And learn a kernel that will give us useful results on the image, and then we can make that image slightly smaller, and then we can apply the fully unrestricted approach when the image gets small enough. All right, so now that I've introduced reinforcement learning and deep reinforcement learning, now I'm going to talk to you about a particular practical application. In particular, I'm going to talk about the DeepMind Atari player. So, for those of you who've never seen what an Atari game looks like, these are several popular games such as Pong, Breakout, Space Invaders, and so on. And this was quite a breakthrough in reinforcement learning because it allowed an agent to play many different games using an identical algorithm and architecture. And it has first been published in 2013 at NIPS, but afterwards it was also published in Nature. The authors used a deep neural network. They've called it a deep Q network or a DQN as an approximator for the Q function that we talked about before. And this builds up on previous successes where a shallow neural network was used to play backgammon. This popular algorithm was called TD gammon, if you want to look it up. So let's see what the setup to the game is. once again, because the typical reinforcement learning setup, we have no prior knowledge about the game itself. The only thing that the algorithm is able to see are these pixel matrices, nothing else. It also receives the changes in score as rewards. So at any stage, it's able to see the current state of the frame buffer, and it's able to receive rewards after performing actions. Actions correspond to joypad inputs, and there is also a special no-op action, which means just do nothing for the next few frames. And there are a few other modifications. In fact, the color information is completely discarded. They used only the grayscale version of these matrices, so we have just one slice into the image, the intensities. We also want to account for the fact that a single frame might not give you the whole state of the world as it is right now. The algorithm uses 6 previous frames at the same time, kind of combined together as 6 different views into an image to give you a more precise view of what the state was a few frames in the past. Another thing which kind of is what made it powerful enough to be able to play many different games using the same architecture is the fact that they squished all the rewards to plus or minus 1. So everything that increases your score is plus 1, everything that decreases your score is minus 1, and everything that keeps your score the same is 0. And this is to be able to avoid scaling issues across different games, because you might have a game where a high score is typically around 20,000 points, but then you might have another game where a high score is 2 million points, and you don't want the network to pick up these variations in different ways. This does take away some power from the model, arguably, for a particular game, but it allows it to generalize across different games much better. And this is what the deep Q network looks like. You start off with your basic image of the frame. You apply a few convolutions, as mentioned before. You then apply this, if it's less than 0, set it to 0 function to all the pixels. You apply some more convolutions. You apply this function again. So in particular, you start off with 16 different convolutions. So you train 16 different kernels that are applied and slide across the image. Then you apply this function. Then you train 32 kernels that are applied to the result of that. These convolutions also incidentally make the images small enough to be processed by a fully connected network. At this point, when you apply the function a second time, you will treat each pixel of the result independently as a fully connected network. So each one is a separate input neuron. And that will then be connected to a hidden layer of 256 neurons. You apply another one of these functions. And finally, for every possible action that you might be able to take, so you can either do nothing or go up, right, so on. For each one of those, you have an output. And this output represents the Q value for that particular action when fed this particular state. That's how we plug in a neural network into that basic Q learning algorithm that I talked about before. There are a few other interesting issues that I wanted to mention here. First of all, because we have a neural network, it has to learn something given known inputs and outputs. So it needs something called a supervision signal. It needs an output. So we have an input, but we have to have some notion of what is a ground truth Q value for it to learn from. And we obviously don't have a ground truth value because we have to learn it as we go along. And what this algorithm does is it uses the formula that we used before for Q learning, the one that updates Q prime, as the thing that the network is supposed to be putting out. So this is not an accurate, real ground truth value. It is something that we believe is close enough to the ground truth value so that the network can learn something useful. Despite the fact that it's not very accurate, it still performs really, really well. So it's just a matter of trying it, and it just happens to work. And neural networks also learn best when their updates are uncorrelated. So you don't want to update based on an input and then update based on that same input, or the same input just changed a little bit. So you don't want to take an action, take the next state and reward, train the network, then take another action, train the network on that. You don't want to do that because the successive frames are going to be heavily correlated. You want sort of to introduce some randomization to the whole process. And what you do is to store a replay memory. So you store the previous n, usually n is like 1,000,000. So you store the previous 1,000,000 screenshots and actions and rewards you've performed. And at every step, you don't train on the latest thing you've done. You train on a random sample of the things you've done in the past. So let's modify the Q learning algorithm we had before into a deep Q learning algorithm. We start off with this empty replay memory. So a replay memory initially has nothing in it. And remember how in the past I said for the Q tables, we can initialize them with random values. Here we initialize the DQNs, the deep Q networks, with random weights as well. And note that there are 2 of them. That's because we don't want to use always the latest version of the network for the evaluation, for determining what our supervision signal is. And this is because it introduces a lot of noise if our ground truth values keep moving. So we want to sort of keep the ground truth network fixed for some number of iterations, and then occasionally just equate these two networks together. So Q prime is going to be the network that we continuously train, and Q double prime is the network that we're going to use to estimate what ground truth values are, and occasionally we're going to set Q double prime to be equal to Q prime as training goes on. We use an epsilon greedy strategy, and the epsilon starts at 1 and it's linearly decreased to 0.1 over a million moves. And based on that, we determine which action to perform in a current state. We receive a reward, we receive a new state, and we add this whole transition into our replay memory. So this is the just basic setup part. Now let's see how to actually do the training. As mentioned, we have a bunch of these transitions sitting in our replay memory. We will choose a small batch of them, just sample a random batch containing these state, action, reward, next state tuples. And we will perform the gradient descent on Q prime, the one that we continuously update. And what is our loss? What is the error that we want to propagate through the network? We start off with what the network is currently giving us. So we take in Q prime, we give it the state, and we give it the action that was performed. This should be AI. And that's the current belief of the network as to what the Q value should be. And this is applying the previous formula, if you remember. This is the formula for iteratively updating a Q table. So we take the immediate reward, we take the maximum Q value, and we scale it by gamma for the next state. But we use this Q double prime network rather than the Q prime one. So this gives us not an actual ground truth of what Q prime should be, but it's something that's close enough for our purposes. So we start off with this value, we subtract it here, and we take the square of that to be the error because we want our errors to be positive all the time. And how do we get these Q prime and Q double prime values? Well, it's simple. You just put the screenshot into the network and see what comes out. And if the next state is not terminal, we'll go back to the beginning. And occasionally, we want this evaluation network to be relatively stable. We don't want it to change every single time. But after, say, 1,000 steps or so, you can set it to be equal to your current network that you continuously update. For the end, I will give you a taste of something that, well, it is no longer cutting-edge reinforcement learning research. The most recent big paper that came out at ICML this year was the dueling DQN architecture by DeepMind, but this is another relatively recent extension from 2015 called the double Q learning, DDQN. And the issue that this tries to solve is, in fact, that if we apply the loss like this, we're going to usually end up overestimating what the Q values actually are. And this is because, if you look at it here, we use this Q double prime network for both selecting which is the optimal action to perform next and for getting the actual value of this action. So we're kind of doubling our bias in a way. So what double Q learning does is decouples this. So it actually uses Q prime to select an action. So it chooses an action which maximizes Q prime from the given state, and then it applies Q double prime to get the value of this action. So we've decoupled getting an action, this alpha, from actually evaluating it for the ground truth value to apply to our network. So this is the essence of what double Q learning is. And it has been shown to give really, really good results and reaching human level of performance or even superhuman levels of performance across many different Atari games. One of the current major challenges actually is to see how good we can do knowledge transfer, because when you learn a network like this to play on a single Atari game, you usually cannot really reuse this network in a useful way on a different game. You have to start training from scratch. But that's not really how humans learn, right? You learn how to play a game, and then just learning how the joystick will move you in a direction should be able to give you some knowledge for a future game. But in this particular algorithm, you cannot really reuse the network that you trained once for a completely different game. You have to start training all over again from scratch. And this whole issue of knowledge transfer is actually one of the current major issues of reinforcement learning. And that was, in fact, my last slide. Thank you.